Welcome to Lecture 13.2 on the definite integral. This is for Math 1325, Calculus for Business and Social Sciences. It may not seem readily apparent, but calculating the area underneath a function, curves, provides an interesting information about the function. Here you can see a curve of a function y equals f of x. The area under the curve would be from the domain from x equals a to x equals b, and is represented by this blue shaded area. In this graph, because it's a curve, we don't really have an easy way to calculate the area. If instead of a curve we had all straight lines, this would be much easier, as we have formulas for the areas of polygons, for example squares, triangles, etc., that are simple to calculate. And remember, with the slopes of tangents, we took slopes of secants, then used limits of these approximations to get to the final point of where we could do a derivative, which was giving us that slope. We're going to do a similar thing here about how do we estimate the area, and then how is it related to an integral. So notice in our first example, we're going to use rectangles to estimate the area under the parabola y equals x squared in the interval from 0 to 1. It's a little bit of a small diagram, but you can see it here. This is x squared, y equals x squared, and it goes from 0 to 1. What we've done is we've divided the interval into 4 sections. So you can see that each x value is 1/4, 1/2, 3/4, and then 1 to get the shaded figure. If we make each of those intervals into rectangles using the right-edged values, so notice for this first rectangle, the height of it is going to be using the right edge to determine the height. Now what that means is we go to that x value, we plug it into the f of x formula, y equals x squared, and that's how tall it is. So for example, this first rectangle is 1/16 tall, because 1/4 squared, y equals x squared, and x is 1/4, so 1/4 squared is 1/16. The second rectangle is a height of 1/2 squared, or 1/4. So notice what we can do. We have the width of each rectangle. They're all the same. They're all 1/4 wide, but their heights are different depending upon the f of x value when x is 1/2, 3/4, etc. So we can calculate all these values, which we've done here, and we get a rough estimate of 0.468, so about a half, right? That the area under this curve from 0 to 1 is approximately equal to a half. Note that the area is the estimate is an overestimate. How do I know that? Because here's the area I want to calculate, which is just the area over the curve, under the curve, but our estimate goes over the functional curve. So we know it's an overestimate. If we use the left end values, the left edge values, notice first of all we don't have a rectangle for the first interval, because f of x when x is 0 is 0, y equals 0. So the height is 0, so our area for that first rectangle would be 0. Here we're going to have an underestimate. Again, we're still going to use the x values, but now we're going to use, for each interval, we're going to use the left x value to calculate the height. Okay, and so we have some difference here, and we can see it's a pretty big difference. It's somewhere between less than a quarter to almost a half. As we increase the number of rectangles, notice we get closer to the actual area. The overage gets smaller and smaller and smaller. Here we have n equals 10, and now we have the area is approximately 0.385. When we go to the n equals 30, or that there are 30 rectangles, we get an area of 0.35. When we go to 50 rectangles, we get an area of 0.34. So we can say that the area under a curve is equal to the sum of the area of the rectangles as the number of rectangles approaches infinity. And so here we have the area equals the limit as n goes to infinity of the sum of all the rectangles. And we do this, R is not for rectangle, it's for right edge values, and L is for left edge values. So either of these could represent a rectangle. It just depends upon if you're using right or left to calculate the area. Note that the width of each rectangle is equal to the interval length divided by the number of rectangles. So here we wanted 4 rectangles. The interval was 1 because it went from 0 to 1. We divided by 4, and that's how we got the area length, right? Or the width of each interval. So 1 minus 0, this is the x values, 1 and 0, b and a are the interval, divided by the number of rectangles we wanted, which was 4, gave us an interval width, or the width of each rectangle, as 1/4, 1 over 4. Okay, so here we have kind of our general formula for the area under a curve. So the area under a curve equals the limit, again, as n goes to infinity, or the number of rectangles goes to infinity, of the limit as n goes to infinity of f of x times delta x. And notice all these pieces is the area of each rectangle, the height times the width, plus the height of the second rectangle times its width. All the widths are the same, all the way up to however many rectangles we have. Curious, this is actually the formula for the area under a curve is actually equal to an integral over a defined interval. Okay, now what does that mean? It means that if we take the interval of x squared from 0 to 1, we will get the actual area under the curve. So let's look at what that means. So a definite integral, we've already done integrals before, but notice now there are values on the integrand sign. Okay, so what these values are the values of the variable we're integrating. In this case it's x, and x is going from 0 to 1. So it goes from 0 to 1. So how do we do this? First we calculate the indefinite integral. Here this is an indefinite integral, has no numbers on it. And we do this the same way. So even with the numbers there, the first thing we're going to do is take the integral of x squared. This is a very simple integral. It equals 1/3 x cubed. And you should know how to do this by now, so I'm not going to walk through that step. This little line here says we're evaluating it from 0 to 1. Now what that means is we plug in the top value into whatever formula is here, and we subtract the plugged in value of the bottom value. So here we have 1/3 1 cubed, the top value, the upper limit, minus 1/3 0 cubed, the lower limit. And that's what we're going to do in each case. And we see here that the actual area is 1/3, which is what we were getting closer to as we kept increasing the rectangles. This is called a definite integral. So when you have an integral sign with numbers on it, it is a definite integral, and it's evaluated at specific values. Okay, remember, an indefinite integral is where there's no numbers here and you just end up with a formula plus c. Okay, now every area of math has a fundamental theorem, and in calculus it's the definite integral is the fundamental theorem. And this is just saying that if we take the integral of f of x, and this equals capital F of x, and we have these limits, then we can find the value of this by plugging in the upper limit and subtracting the lower limit. Okay. So now it's really just time to practice. This might be where you want to hit pause. We have several simple integrals, definite integrals here. So the first thing we're going to do is take the integral, and we get x to the 4th over 4 plus 4x plus c, evaluated from 4 to 2. Now notice the c's are going to cancel out, plus c minus c, so they go away, so we don't really have to worry about c in any of these definite integrals. We plug in 4 for the upper limit into this equation, 4 cubed plus 4 cubed, I'm sorry, here it is. Let me start over. 4 to the 4th power over 4 plus 4 times 4 plus c, and that's what we have here, minus the lower limit where we're going to plug in 2 into this equation. So 2 to the 4th over 4 plus 4 times 2 is 8 plus c. Again, we have plus c minus c, so those cancel out. When we do the math, we get 80 minus 12, or 68. It really is a good idea for you to try to do these on your own, not just watch. It's very hard to assess whether you're getting it or not until you try one. So with this next problem, go ahead and hit pause, do the problem out, find the integral, that should not be a problem, plug in 3, calculate that value, plug in 1, calculate that value, and then subtract it, the value of 3 minus what you get for the value of 1. So when we take the integral, we get x cubed plus 3x squared plus c, and again we're evaluating it from 3 to 1, so plug in 3, plug in 1, and then subtract those. And here we get the value, we get the value of 50. And again, I'm not going to walk through this. It's pretty straightforward. It's just plug in and play, so to speak. The good news is that all the integral rules that we learned before, that we can, if we have a sum or a difference of functions, we can separate them and do each piece. If we have a constant times the function, we can pull that constant outside. We can still do that. Now we have some that are specific to definite integrals. Notice if we evaluate an integral from over the same point, from point A to point A, we get that this is equal to 0. And that kind of makes sense, because if you plug in A and you're subtracting the values when you plug in A, of course it's going to be equal to 0. But also conceptually, remember a point really doesn't have any kind of mass or area, so the area under something that has no mass should be 0. Okay? Another interesting thing is if we're looking at a function over an interval AB, that the value of the integral from B to A is equal to the opposite of the value if we switch the limits. So notice here we have the limit from B to A, and here we have from A to B. And so the values are the same, absolutely, but they're opposite signs. All right, so let's look at a more difficult problem, and this is going to wrap up our lecture for the day. Let's look at a more complex integral. So this gives you a little more practice, really, with integrals complex. This isn't extremely hard. Remember, with the power rule, we substitute u equals whatever's being raised to a power, and then we see if we have du in the problem. Here, when we take the derivative of x cubed minus 3x squared, we get 3x squared minus 6x dx, which is not exactly there, but notice if I factor out a 3, I do have that part. So remember that I have everything here I need except for the 3, so if I add the 3 inside, I have to add a 1/3 outside. Okay? Once I do that, I can then take the integral. Now, I haven't shared another interesting thing here, and I hope I've got this in my notes. But remember, these limits are the values of x. Often it is actually easier when I convert the formulas into a substitution of a u formula to also convert the limits into u as well. And what does that mean? So I put in here that the limits are still connected to x. Well, we've changed what our variable is in here from x to u. So if I knew what these values were for u, I could just plug them into here instead of going back and having to rewrite this formula. Okay, so we'll look at that in a minute. Let's finish solving this, and then we'll see how much easier it is if I change the limits to equal to u. So here I get, this is my integral, 1/12 x cubed minus 3x squared to the 4th, evaluated from -1 to 2. So I plug in the value of 2, I plug in the value of -1, and I subtract them, and I get 0. Interesting. Okay. Now, what did I mean about changing these values to u values? Well, remember up here we have done a substitution that u equals x cubed minus 3x squared. So if I put in x equals -1, I can find the corresponding u. So when u equals 2, when x equals 2, u equals -4. And when when x is -1, u is also -4. Notice that I can plug this into my simplified integral that we solved, and it's a much easier equation. And in fact, if I plugged it in here, I should be able to stop. Because remember what happens when we evaluate an integral over the same point? This is a rule or a property that's certainly going to be 0 because there's no area under a point. Anyway, that's the lecture for definite integrals. They're pretty straightforward. Remember that if there are numbers here on the integral sign, you want to have an answer that is a number. If there are no numbers here, then your answer is going to be of the form of the integral or a function with a plus or plus constant. All right, hopefully this helps, and that it gets you prepared for the next lesson. Have a good day.